Okay, welcome to our second installment. Today we're going to do a little algebra. This is my Sage intro series, and this is brought to you by CalcPage, the Calculus and Computer Science Archive online on YouTube. Also is brought to you by shadowfaxrant.blogspot.com. All right, so let's log in like we did yesterday. Let's go to the Alpha site. Use your username and password from yesterday. There's that. And actually, no, I think it's this. Yeah. And we're in. I don't want that. Something I was playing with. Go away. Come on, go away. There it went. Okay. Let's create a new worksheet. New worksheet. Load, load, load. Load, load, load. 1 minute down and counting in our YouTube recording for today. Here we go. So I'm going to call it Sage, Software for Algebra and Geometry Exploration. 102, our second installment. And how about we do some algebra? Ta-da! So let's start with something easy. How about we factor x squared plus 2x. Now be careful, multiplication has to be explicitly spelled out. Alright, so that's shift 8 for times, plus 2. And is that factorable? Well, let's find out. I don't think so. Not over the integers anyway. What multiplies to 2 and adds to 2? I don't know. So the answer will be unfactored. Okay, but you know, this probably does have some roots. How about we do solve instead? Let's take the same thing and do a solve with respect to x. So solve that equals 0 equals 0 with respect to x. Okay, equals is a Boolean operator. It returns true when the left side of the equation equals the right side of the equation. What solve does is it finds an x value that makes this true. Single equals is an assignment operator in Python. It makes the left side, it stores into the left side what's on the right side. That's not what I mean here, so I'm not doing that. And let's see, what are the roots? And these roots are, I think they're complex, aren't they? Yes. -1 minus I and -1 plus I. Or however they wrote it, that's nice. Don't forget you can do typeset if you like. Come on, typeset. There's your pretty print. There's your pretty print. Okay, so since I can't factor, I don't know how to factor a quadratic or in terms of complex numbers in my head without a quadratic formula or something, I'll say that's not factorable. All right, let's factor something else. Let's try the same thing, but change it just slightly. I'm going to put a +1 here. Now I think it's factorable. I think, in fact, if you do the discriminant, b squared is 4. Minus 4 times a times b, 4 times 1 times 1 is 4, 4 minus 4 is 0. You have real rational equal roots, so that this is factorable and the two factors are the same. X plus 1 times x plus 1, perfect, very nice. Let's change it up again. I think instead of +1 I'm going to have +0, and that's a greatest common factor of x. Let's see if it takes out the x for us. Yes, it does. Very nice. Okay, let's change it up again. I just did, by the way, all I did was I highlighted this with the mouse. In case I'm going too fast for everybody, Control C for copy. And then I went down here and did a Control V for paste. Okay? Now I'm going to do, let's see, I did a 2, a 1, and a 0. How about a -1? -1. Now if we do the discriminant, b squared is 4. And 4 times 1, 4 times a times c, 4 times 1 times -1 is -4. So b squared minus 4ac is 4 minus -4 is 4 plus 4 is 8. That's going to be real irrational unequal, isn't it? So it's not factorable over the integers. But if you do a solve on that, let's see, let's solve that. I think you're going to get irrational, real irrational unequal roots. Let's see. Solve that when it hits the x-axis. Okay, and we're going to solve with respect to is x, and do we get irrational roots? Yes, we do. -1 minus red 2 and -1 plus red 2. Or as Sage likes to write it, negative red 2 minus 1 and positive red 2 minus 1. And, okay, there you go, that's good. What about factoring other stuff? How about this one? So we did a greatest common factor, we did a quadratic. How about a tricky try, or a master product algorithm? Like, let's see, 10 times x squared plus 11x. Let's see, plus 11x minus 6. I think that's factorable. Let's see. What multiplies to negative 60 and adds to 11? Multiplies to negative 60 but adds to 11. Let's see. Come on. So it's, I think what it did was, let's see, I'm going to make this a comment. I think what we did was 10x plus something, I don't know what, times, this is a comment, so it's not going to run this, okay? So this is just like note to self. 10x plus something else divided by 10. Now what are those two numbers? Two numbers that multiply out to negative 60. Let's see, negative 60, and I'm not going to save this, so I don't even have to comment this out. I'm just going to, just write stuff. It multiplies to negative 60, but adds up, let's see, the product is negative 60, but the sum is positive 11. Let's see. So what multiplies to negative 60? Well, negative 1 and 60. Now that multiplies to negative 60 and it has a positive sum but not 11. Okay, how about negative 2 and 30? The sum now is 28. Okay, how about negative 3 and 20? Now the sum is, what is it? It's 17. How about negative 4 and 15? Won't that work? That multiplies out to negative 60 and adds up to positive 11. Okay, so that's what it did. We added a negative 4, we subtracted 4, and we had a positive 15. Okay, so that's how you do master product algorithm or tricky try. And hopefully what happens is this reduces a little bit. There's a greatest common factor of 2 here. Alright, so if I take that out, it's going to be 2 times, what, 5x minus 2, right? 5x minus 2. And look, that's what we have here. I'm just trying to understand where this came from, okay? And this has a greatest common factor of 5, doesn't it? So if I take out a 5, and what's left is a 3x plus, 2x plus 3. And then when we divide by 10, the 10 reduces with a 2 as 1 over 5, and then the 5 cancels with 5 over 5. So all that's left is exactly that. All right, so I'm going to delete this. But that's where that came from. Good. So we know how to do tricky try. How about difference of two squares? Let's do factoring of something silly. How about x squared minus 4? Of course, that's going to be x plus 2x minus 2. Let's see. And there it is. What about a difference of two cubes? Factor. Let's see. X cubed minus 1. That's a difference of two cubes, isn't it? Let's see. Let's bring this up a little bit. And it's evaluating. Isn't it going to be x minus 1 times something? Yeah, there it is. How about the sum of two cubes? The same thing, but adding. Alright, now it's going to factor out an x plus 1, right? It's always the cube root of x of this guy. X cubed's cube root is x, and the cube root of negative 1 is negative 1, or the cube root of positive 1 is positive 1. Then if you square x, that's this part, and if you square the negative 1, that's this part. And if you multiply the x and the negative 1, you get negative x, but you subtract it. You multiply x times 1, you get x, and you subtract it. That's the pattern. Alright, that's great. What about something a little bit more crazy? Factor. Let's see, what do I want to factor? 27x cubed. 27 times x cubed minus 64. This is still a difference of 2 cubes, right? The cube root here is 3x, and the cube root here is 4. So the first factor will be 3x, and the factor, and the cube root of negative 64 is negative 4, at least the principal cube root. And so, what do we get? Right, now if you cube that, if you square that, you get 9x squared. If you square that, you get 16. If you multiply this times this, you get negative 12x, but if you subtract it, it's positive 12x. Yep, we know what we're doing. We're good at this. What if I want to factor something like this? Factor, let's see, factor what? Factor, let's see, 125 times x cubed, okay, plus 8 times y cubed. And we're going to get an error. The thing is, you can use any variable numerically, but algebraically only x is defined as an algebraic variable. If you want to use y algebraically as a symbolic variable, you have to define it that way. Var, like this, var, quote, y. Now let's see if that works. And let's see, we should get 5x and 2y, yep, and we get 5x squared, yep, and we get 2y all squared, yep, and we get 5x times 2y is 10xy, and we subtract it. Right, good, very good. What if we don't have, like, just to the third power? What if we have something crazy? Let's see, how about we want to factor, let's see, x cubed plus y cubed. Well, first of all, is it still defining the y? I think so, yes. Okay. Then let's go nuts. How about to the 33rd? Whoa, look at that. That's crazy. How about to the 99th? Oh, it's working. Wow, look at this symbolic algebra this thing can do. This is a computer algebra system at work. Now, if you don't want to look at that way, you want to turn off the pretty print. Okay, let's go up here, turn off the typeset. And let's see if we can see this all in one cell with like word wrap or wraparound on. And we get a lot of stuff. Wow. If we go back to when it was 3, we're going to get that, right? And then when it was 33, we're going to get that. And then when it's 99, we're going to get stuff. There it is. How about 999? Because when you factor to get more perfect cubes and stuff like that, it just keeps on getting bigger and bigger and bigger. And what do you get? Holy cow, are you kidding? Well, I'm not going to read all of that. You could run it and look at it on your own machine. And if you like pretty print, you can go back to it and see it all in one line. But then we've got to slide over. Oh boy, look at this. Do it. Yes. Nope. Yes. Nope. Yes. Ooh, what happened? Oh god, did I kill it? Oh, there it is. So you got the x plus y, and then you got x squared minus xy plus y squared. Then you got, oh my goodness, look at this. This is really ridiculous. Oh my goodness, look at this ridiculousness. And to do that by hand with pencil and paper, you would be there for a while, okay? So let's not say we did. Alright, what else do we want to do? Well, I mean, you can factor numbers too, you know? Let's see, factor 1, 2, 3. Is that factorable? And it is. Remember 127 was a Mercine prime. Let's see, what happens if we put in a prime? There you go. So that's factorable because the digits add up to 3, so 3 goes in. That's factorable because it ends in an even number, so 2 goes in. That's factorable because it ends in a 5. 5 goes in. Or 5 or a 0 should be factorable, right? Okay. How about this? 6, 7, 8, 9, and 10. That's factorable because it ends in a 0. It's not prime, in other words. Wow, that's crazy stuff. What if you want to go a little nuts? I don't know. 1 2 1 1 1 1 2 2 2 3 3 4. What's that going to do? Yeah. Okay, I knew that. And of course, if you're going to factor a machine prime, look what happens. Factor 2 to the 2 minus 1 was machine, right? That's 4 minus 1 is 3, and it's not factorable because it's prime. 2 to the third minus 1 was machine, so it doesn't factor. It's already prime factors. It's already prime. What if I put in a prime exponent, a machine prime exponent, and it just calculates the number? Okay, good. So we know how to factor. We know how to solve. Did we do all those solves? Let's see. What if I do solve? Again, x squared plus 2x. Remember, times x is explicit. You got to say it. Plus 2 equals 0 for x. I think that was the complex case. So you get the i's, right? All right. Let's do the same calculation. And let's make it plus 1. That was real rational equal case, I think. So there was one root. And plus 0, or just get rid of that stuff. That was real rational unequal. Yep. And minus 1 was real irrational unequal. Right? Okay, good. That sounds good. So we could do stuff with quadratics and whatnot. We could even graph that and show you why the roots are what they are. This graph doesn't hit the x-axis. This graph just taps. This graph hits at 2 points on the x-axis that are easy to find, and this one, 2 points that are not so easy to read off the graph. Let's see. What if you plot x squared plus 2 times x plus 2? Okay, and I don't know. These are relatively small roots. I want to see where they are. How about we go from, I don't know, negative 2 to 2. And let's see, do we get a graph? And this is the complex case. In other words, it shouldn't hit the x-axis. Let's see that that's the case. There it is. Now you can do separate plots, but if you want to put it all in one, I could say, okay, comma, x squared plus 2 times x plus 1. Now that's an error, because if you're going to plot more than one function, you have to make a list, and that requires parentheses here and here. There you go. And let's see, this one is the one that was real rational equal, hits the x-axis at one place. It was at negative 1. There it is. Good. Very nice. Okay. What about, by the way, I think if you can specify which variable, can't you? I think so. So this is like on the TI graphing calculator, TI-83, TI-89, TI-84, TI-92. This is your x min and your x max, and it'll figure out your y min and your y max accordingly. Let's throw in the one which was real rational equal. No, real rational unequal. Okay, so that was x squared, adding to the list into the parentheses, plus 2x, 2 times x, be careful, you can't do implicit multiply here, plus 0, or just leave it blank, and this hits the x-axis in 2 places now. Does it not? Yes, it does. And I hesitate to eyeball it, but it does look like 0 and negative 2, which is what we got before. To get a more exact answer, you write a program to do the quadratic formula, or you do the factoring, or you do the solve, and that's this one, 0 and negative 2. All right, now what are these roots? Let's see. Rad 2 is about 1.414. Minus 1 is 0.414. So you should see it hit here. And this is negative 1.414. Minus 1 would be negative 2.414. I should see it, well, not in this window. Let's add to this. Comma, x squared, let's see, comma, x squared, what was it? Plus 2 times x minus 1, I think it was, right? And that should give these roots. Now these are the exact roots. Let's see them graphically. There they are, about 0.4 and about negative 2.4. I don't see it. How am I going to fix it? Change this domain. How about -3? That should do it. And there you go. So about positive 0.4 and about negative 1.4. You're not sure about that? Well, how about we write it this way? Let's evaluate. -1 minus the squirt of 2, the squirt function. And let's see what we should get. And that's pretty print. I need a numerical result, so let's do it. And now we could go crazy with digits here like we did yesterday and show that this is an irrational number. The digits do not repeat. Let's do 100. There's no pattern, discernible pattern here. Is there? Let's see. Dun, 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 dun. Right? I mean, look at it. And if you don't want pretty print, you want to see it all in one cell, you can turn it off and reevaluate. And there you go. And if you want to go crazy, but the point is, it is negative 2.4 something, right? And there you go. I mean, look at this. There's no pattern, repeating pattern here. Let's do the same thing, but now it was -1 plus red 2i. -1 plus red 2. So I'll just copy that, highlight it with the mouse, Control-C to copy, click in here, Control-V, and make it plus red 2. And that was the one we said was about 0.414 something. Let's see what we get. 0.414 something, but there's 1,000 digits for you, just for fun. Yes. Now if you put pretty print on, let's see if we can get that in a slider, the whole thing in a slider. And there it is, and you can just slide, 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 slide. Wow, that's crazy. That's amazing. Okay, you can also expand stuff, you know, like FOIL stuff out. What if I wanted to do, I don't know, quantity x plus 1 to the 0? That's going to be 1, right? What if I wanted to do the same thing, but to the 1? Well, then it's x plus 1, isn't it? But what if I did it to the 2? Then you're squaring it or foiling it, x plus 1 times x plus 1. X plus 1 times x plus 1. But I want this expanded. All right, so use expand. Expand it. There you go. What if you take that same expression and you cube it? And now you start seeing Pascal's triangle, right? The coefficients 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. You can start talking about the binomial expansion theorem and sigma notation, all kinds of fun stuff. How about we write a program? Here we go. For, whenever you have sigma notation, you're talking about a for loop. For I in range. Now, how do I get these numbers? I want to plug in 0 through 3. So I think the range has to be 0 to 4. 4 really means, in this case, I have 4 numbers I'm plugging in. 0, 1, 2, and 3. So I only get integers from 0 to 3, really. I don't get the 4. Colon, enter. And I'm going to show. Show is like pretty print and centering all at once. Okay, so I'm going to have a Pascal's triangle that's like centered, I think, if I recall correctly. Quantity expand. So even if you don't have pretty print on, show will make it so. Let's see. Boom. Let's see if we get pretty print and centering, I think. Expand what? Well, this same expression, it's going to be quantity x plus 1 to the, but now the x wanted is I. Let's, we close the x plus 1, let's close the expand, let's close the show, and let's see what you get. Dun 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 dun. Today would be nice. Yellow. Yellow. There it is. See how it's centered and everything? Okay, so that still has pretty print if you use show. Let's go one more. Come on, you can do it. Alright, so look, you got the 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. You can start talking about factorials and combinations, permutations, formulas, all kinds of crazy stuff. Let's go completely nuts. Alright, there you go. Isn't that nice? You don't want show, you want to do print. Then it doesn't center it, but you still have pretty print on, or do I? No, I don't have the pretty print on. I could keep pretty print on if I want. And see what that does. So it's not centered. What happened to the pretty print part? Did I put it on? Yeah, that's not pretty print. Hello. Maybe, well, maybe print supersedes that. What if I don't put a print? What happens? Let's play around here. Oh, there you go. So print supersedes pretty print, and show supersedes not pretty print. How's that? And show also gives you a nice centering and whatnot. Okay, how about we go, I don't know, 12. So we got the pretty print, but we don't have the centering. See, with the centering, it's a problem because when this gets really, really big, it centers based on the longest line, and then you may not even see the other guys. Right? Look, let's do a show. So that'll add the centering. Actually, I already had parentheses there, so I don't need them. See how it's centering based on the last line? So if it gets really big, look what happens. If I go, I don't know, 20. Let's see, about 20. Then it's hard to see what's going on over here, see? Yeah. So I don't know if I want to do a show. I'll keep the pretty print on. These parentheses are optional. You could leave them or take them out. And now let's see what happens with the pretty print on, but not the show, so it's not centered. That is pretty print on, right? Yes, it is. Typeset is on. And there you go. And so there's Pascal's triangle, the coefficients anyway. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 6, 4, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, and so forth, all the way down to there. Then you start talking about what happens if you change this up a little bit, put a little negative. I'm not going to get this crazy. How about 12 was big enough? Maybe 15. See what happens when you throw in some negatives. The signs start alternating. What if you put in some coefficients other than 1? Then you get craziness going on here. And we could talk about that using the binomial expansion theorem. I'm not going to get into that right now. What if you put in 9 here? And to the 0 it's 1, and to the 1 it's 2x minus 9, and to the 2 it's that foiled out, and so forth. This all makes sense. It's just starting to get a little crazy. Ding, 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 ding. Alrighty. If I restrict myself to, I don't know, 9, and I put show on, well, I should be able to see most of it. And yeah, pretty good. Yeah, close enough. You can slide around a little bit if you need to. Okay, so that's a little bit of algebra for you. You can also do, let's see, what didn't I do? You could also do, you know, function notation like in calculus and pre-calculus. You can do a little calculus. Look, what if I said f of x itself is defined as the expand of quantity x plus 1 to the 6th, and let's, now if you just do that, it defines f of x, but it doesn't show it, so I have to do this to show it. I have to type it again, and that's just shorthand for 2 lines, 2 commands. Show it, show it, show it. What happened? There it is, right? And we have pretty print on and all that. This is just shorthand for doing this. So the first line defines f of x. This one actually prints it out, and it's like a show without centering because I have pretty print on. I can evaluate that function if I want. F of, I don't know, negative 1 is apparently 0. I just guessed at that. I didn't know it was going to be a 0, but if f of negative 1 is 0, then x equals negative 1 is a root. So x plus 1 is a factor, and then you can divide this away if you wanted to. Let's see, what if we did, yeah, how about we take f of x and divide it by, yes? Yeah, I'm recording right now. So let's see, there you go. What if we divide f of x by the x plus 1? Should be an exact factor. And it doesn't do it. So how about we make it so? Would expand help? Ugh. How about, what if I factor f of x first and then divide it. Let's see, factor. Let's see what happens. Okay, that's true. Right, because it's a power of x plus 1. But if I want to then expand that, oh, so I knew -1 was a factor anyway. Duh, that was silly. -1 was a root, so x plus 1 is a factor. But there you go. Okay, so you get to talk about rational roots theorems and synthetic division and all kinds of crazy stuff. What if you want to differentiate this thing? Let's see, f of x is a 6th degree. What if you do f of x dot diff? That should be a 4th degree, right? Yeah, okay. Let's see. Right, and f of x is x to the 6th something, so the derivative is 6x to the 5th something, so that's good. All right, you had a slight interruption there, that's okay. Now, if f of x, we sort of joke around in calc class when we do motion problems, if this is like f of t, is a displacement problem. The first derivative is, if that's a displacement function, what happened? Wait, could I do this? No. Or maybe I could do this. Alright, so that just substitutes t in for x in f of x, right? So if I do this, now, okay, so this is a displacement function is a function of time, t, and the first derivative is the velocity. The second derivative would be the acceleration. The third derivative, we call it the jerk. And then we run out of names real fast. So how about the first, second, third? The fourth derivative, let's call it the snap. And the next derivative, the crackle. Now, first, second, third, fourth, fifth. The sixth derivative is the pop. And the next one, I don't know what to call it. It should be 0. And that all makes a lot of sense. Very good. So a little differentiation, a little function notation. Let's see. What if we said let g of x be f of x dot diff 2? I think what that does is it gives me the second derivative. And again, it's not going to display it unless I type g of x. So it's just going to define g of x. That was silly. How silly of me. Okay, let's display it. And so, is that the second derivative? Let's see, let's go back, let's get rid of this. And it is, but this is in terms of x, okay. And so I could then evaluate it at a certain point if I wanted to, at x equals 1, and so forth. I could integrate too. Remember f of x? Okay. What if I do f of x dot integrate? With respect to x. Here we go. Now the integral of x to the 6th with respect to x is x to the 7th over 7. There you go. Want to integrate again? With respect to x, it'll take this and make it x to the 8th over 56, right? Let's see. And correct. There you go. Perfect. If you want to do a definite integral, a numerical integral, you could say f of x dot integrate from, I don't know, 0 to 1. What I did? I did something stupid. Variable of integration should be specified explicitly. Really? Is that so? Okay, with respect to x, I guess. There you go. Okay. If you want the numerical version of that, that's fine. Look, if you only do the integrated once, you get that. And if you plug in 0, it drops out. If you plug in 1, you get a 7th plus 1, plus 3, plus 4, plus 5, plus 5, plus 3, plus 1. Apparently that's what that is. Let's see. Is that true? Let's see. Let's plug in. The fundamental theorem of calculus says plug in b, f of b, cap f of b minus cap f of a. A is 0. So that drops out. So what's cap f of b? It's apparently, if you plug in 1, it's 1/7 plus 1 plus 3 plus 5 plus 5 plus 3 plus 1. Evaluating. And yeah, it's the exact same thing. And if you like a decimal version, of course you know what to do. There it is. You know, you can do, let's see, you could do all kinds of integration here. You could show partial fractions. Let's see, what if I let h of x equal, oh, I don't know, let's see, x plus 1 divided by x squared plus x minus 2, which is factorable. I think, if you can factor the denominator, you should be able to do partial fractions out of this. Let's see, divided by, let's see, x squared plus x minus 2. And let's show h of x. There it is. Now, what if I want to factor it? Let's see, let's do this. Let's factor it. There you go. Perfect. All right, so that's an integration by parts problem. So if I do h of x dot integrate with respect to x, I would expect something to do with an ln of x minus 1 and an ln of x plus 2. And remember, log in Sage and in Python really means ln, or log base e. So that sounds good. And we could show how to do that on the side, but maybe not right now. What about a integration by parts? What if I let f of x, let's redefine f of x as, I don't know, x squared times e to the x. And let's integrate that. Well, let's see, let's show it. There it is. Okay, so if I integrate that, this should be integrable with, you know, tic-tac-toe. Anyone know tic-tac-toe from Stand and Deliver? That integrate with respect to x, and that's a typical integration by parts result. Yes. Okay, that sounds about right. Okay, I think we've done a good enough of introduction to sort of algebraic approach in Sage. So I hope you got something out of this, and this keeps you busy for a little while getting used to using Sage. Thanks for tuning in, and see you tomorrow. Bye-bye.